since I'm not online, maybe I should start it here. I have one question. Maybe you could just, if I manage to start it. I have one. Socrative. Let me see. Here we are. Give it one try. You're up and running. One nice question. My last part is actually related to this question a little bit, but I already talked about it. We have a term, that looks pretty nasty. We have the term colinearity, and then we raise a warning sign, because then we might need some more classes to really get all of it. But for now, it's a warning sign. We need to be worried about or think about the consequences of the situation where the different x's in our multiple linear regression model themselves are related to each other. That's what we mean by colinearity. That's the term. That means that the different x's potentially themselves are related to each other. We saw that actually. That maybe we didn't study it in detail, but I assure you that if you study the relation between like temperature and wind, or definitely wind and ozone, wind and radiation, sorry, just to make the point. The x's are related to each other. That should make us be extra intelligent and careful about how to interpret results from MLR models. Now, we try to construct a little example here to make the point explicit. Let me, as I usually do, just say a few words while we look at this. Pretty terrible slide, but still a bit colored to make us maybe see something nicer than in the R. I'm trying to generate a situation for you here with 100 observations. I'm having some odd x1 and x2 that I'm plotting, and then I'm simulating a relation to some y, and I'm trying to see what happens if I do the linear regression in that case. Let's see if it works. Here. The heading says, we should try to understand, I'm trying to make us understand what our challenge is here. The x is kind of a sine curve like that. The x2 is also a sine curve. It was actually simulated to be almost as x1, but a bit of noise. So it's not exactly x1, but it's a kind of a noisy copy. So x1 and x2 are noisy copies of each other. Very common data in many contexts. If you have chemical spectral data that you have in many contexts, such situations will occur very often. And the consequence of those two x's being highly correlated, both of them a sine curve, but means that if I look at the sort of the linearity, the relation between x1 and x2, right? It's not the y thing, it's just the two x's. They themselves are highly linearly correlated to each other, right? That's the situation we should think about. Then I'm simulating some y's. Which y's am I simulating? Something with an intercept and a relation both to x2 and x1, with a beta 1 of 1 and a beta 2 of 1, and then a sigma of 1. So I'm having some y's with the relation, not surprisingly then, since they have been simulated like that, that when I plot y versus x1, it's a bit like our ozone versus temperature, ozone versus the other things, right? Y is, of course, linearly related to x1 and x2 with a bit of noise, the sigma of 1 that I put into it. Now my question is, and the question in the Socrates quiz is related to what I'm going to share with you now. What will happen? What will happen now if I do the obvious that I would like to do? Where I fit the multiple linear regression model with y depending on x1 and x2. I could do it again. Slightly nicer example to make the point. I said sometimes we hit the limit for a pedagogical point to make. What is the conclusion of x1 in this model? Does x1 have an impact on y? No. It's non-significant, clearly non-significant. Does x2 have an impact of y? No. What is going on now? Is there overall, we don't talk about this in the e-notes because we don't use it very often, but I can share with you, is there overall a relation between y and the two x's seen jointly at the same time? That's the hypothesis test at the bottom. Don't worry, it's not something that you're supposed to know about. But you can see this p-value is extremely. So this one expresses what our gut feeling is telling us, right? Yes, there must be a relation between y and the x's. And the conclusion down there is, if I make the hypothesis, both beta 1 and beta 2 are 0 at the same time. That's the hypothesis which is tested at the bottom. A two-dimensional hypothesis, you could say. If I test that one, I can conclude, whoa, that's definitely not true. But if I test each of them individually in the MLR model, they're non-significant. How can that be? It makes sense, actually. But we just need to, my point is not to show you that the model is doing something wrong for us. We just have to understand what is going on here to be able to be fully up and driving the car here. Otherwise, we might hit something when we go around. I heard the discussion about self-driving cars this morning again, the ethical thing. Should it save you or should it save the 20 children in front of you? and whether you would like, maybe they should have an option. Should I be in the ego mode or in the altruistic mode? That's the discussion also. If you want, you can offer yourself for the greater good. Anyway, sorry for the... It makes sense. It makes sense because x1 and x2 are copies of each other. The interpretation of the... Also look at these coefficients. They are not 1. They are far off 1 somehow. But also look at these standard errors. They're very, very large standard errors, which of course makes the thing become non-significant. The thing is, there is not room for both of them there, right? The MLR interpretation, which is the nice one, is that we try to estimate what is the effect of x1 having already used x2, that is given a fixed value of x2. Is there then an additional effect of x1? No, there is not. That makes sense. x1 and x2 are copies of each other. When x2 is in the model, we don't need x1, right? So x1 conditioned on x2 is not important. And vice versa. When x1 is in the model, we don't need x2. That is what MLR is telling us. When you have the other one in the model, I'm not needed. So both ways, they're not needed, given that the other one is there. But don't throw away both of them. Then you're into trouble, right? This is why we, as a sort of idiot-proof approach, tell people and never throw away more than one variable at a time. Because you may miss some of these important things. Of course, there are many tools out there to deal with this. But that's for future multivariate analysis courses for you to take. It's a complicated challenge, but interesting one, and extremely relevant one, with the amount of data hitting us. Now, both in terms of variables and in terms of observations, we get to millions in both dimensions. Now I'm just having 2, and I'm still already having a problem, right? So if I have 1 million, so go take classes on multivariate data handling of various kinds to be better at this point. But now we start here. Start to understand some of the challenges. The point is, these guys on the soccer data, they had maybe 10 different, they had x1 up to x10 to choose from in the data set. And how many different choices out of 10 can you make? That's a large number. And at least enough to have the 29 groups to make different choices, each of them. Anyway. The last part of this example is to say, this is a consequence, this type of data is a consequence of the real life situations that might hit us. That's just the way it is sometimes. Maybe you record things that are the same. And sometimes if you do have spectral chemical data, NIR spectral or other sorts of spectral data, I mean, there are a lot of copies of the same information along the wavelengths in an NIR spectrum, for instance. So you may have 1,000 wavelengths, but you just have basically 2 variables, like that. So inherently, that's a practical challenge that will meet us, that will hit us. Such regression models are used in Lundbeck and other places to predict things in the production line. However, if we are in science, if we were really interested in the individual effect of x1 and x2, right? x1 corrected for x2 and x2 corrected for x1. The problem of the data set we were facing just now was we do not have the information about that in our data, right? We just have a single line of x1 and x2 data. We don't have information about how they can individually affect y. Because we don't have the data, we didn't expand the X space to include enough information of X1 and X2. That's why designed experiments are used a lot. Definitely in the medical industry, but also in other. If I can design the experiments, I can make sure that I have a good distribution of the X1 and X2, sort of span the whole thing independently. For instance, let's see. Like that. The point is, now I have, you can look at the details later, but the point is, I made an x1 and an x2 here. The point is, I took the sine curve first, and then I put it at 0, and then I took the sine curve at the first part, I put it at 0 at the rest. I constructed an x1 and an x2 such that the correlation between x1 and x2 are now 0. That's the core point, right? Before the correlation was 0.9 or so between the two x's. Now, they sort of, at least given the structure they have, they span the whole space. Not randomly, but independently. Then, if I do the same exercise, look at that. It's the same x1 and x2 structure. I just made an experiment where I decided how to design the x1 and x2. In the first half of the experiment, I kept x1 fixed and only let x2 go like that. In the other part of the experiment, I did vice versa, right? So I controlled the experiment to give me all the possible combinations of x1 and x2 in an independent way, in a structured orthogonal, as a mathematician would say, in an independent way. Then I can estimate the effects of x1 and x2 separately, sort of independently of each other. And I get the right results, you could see, right? Both of them being significant. So design experiments, when possible, are of extremely high value, right? There's a big difference between setting up studies on your own and just observing the nature. Observing the nature can be good and necessary. There are limits to what we can do experiments about, but whenever it's possible to design them yourself, then you can identify such effects that you might not otherwise be able to identify by just studying the nature, because they co-vary, they are collinear, potentially, the different x's. It's pretty complicated, this, right? So don't worry. This is towards the future for you, all these thinkings. It's just to say, we should have a look at the Socrates. How did you do? Have you done it? To my knowledge, green should be the good one, right? Oh, yeah, my goodness. What am I going to do with you, for you? Where do we see let's finish. Let's get a report. Whole class Excel, no. Individual students, PDF, no. Question specific, yes. Download. Now, let's just spend 2 minutes talking about this. I tried to construct a situation that's similar to the one I just discussed here at the end, right? But put into the height-weight story. And I mean, I don't show you the actual data. I'm trying to speculate that I'm going to use not only the height, but also the shoe size of all of us to model and predict the weight. My sort of scenario that makes my answers become what I'd like them to be is then that I expect that shoe size and height in centimeters among us are highly correlated. Not with a 1, but highly correlated, right? So I assume that there is not a room in the model for both height and shoe size to predict weight. But definitely, of course, individually, height will be closely related to weight. We've already seen that. And similarly, if we just take shoe size and try to predict the weight by shoe size, yes, it will be related. Question? Because of, I mean, we could argue and look at, there are no numbers. So I'm using the example that I just showed you with the two x's highly correlated. And we saw there explicitly that there was not room for both of them in that example, right? But when I say that, I mean that none of them was significant in the example I just showed you. And now I'm saying I'm having the same thing in mind here. That if shoe size, let's just speculate that shoe size and height of us are exactly correlated, almost exactly, then you couldn't identify an additional effect of height given your shoe size. If you take all people of shoe size 40, they're exactly the same height then. And you wouldn't be able to identify what is the potential additional effect of height, if there is one. You are trying to estimate the unique effect of height for people with the same shoe size, but you basically, the data gives you no information about that, right? Because you only they only come in all people with that shoe size are the same height. So how could you identify what the additional height thing is? You don't know. It's not part of the data. And it will come out as two non-significant results. So, y depends on height, yes. Y depends on shoe size, yes. Both of them will be clearly significant. I've sort of expanded the statement a little bit to be sure that it would be wrong. Both of them would be clearly significant if I put them in both. No, they will not, because as we've just talked about, right? Like the example I just showed you, I will not expect them both to be clearly significant. Most likely both of them will be non-significant. It depends. Sometimes it's a mix, of course. Sometimes it's a blurry. Maybe they're both collinear, but still there could be an additional unique effect. And maybe we have some information about it, but not completely. I mean, I'm just talking about the pure problem and the pure points here. And then, probably the height has no effect when the shoe size is in the model. Yeah, that's exactly what I said. Probably the shoe size has no effect when height is in the model. Yeah, I agree. 4 out of 5 was correct. Many of you had some correct. So don't worry. This was the first time, and basically you heard about it while answering, so I'm happy. You also, be happy. Enjoy it. See you.